Hello statistics students, this is Jamie Amy, and this video is our discussion on chapter 5, which is on probability distributions, and section 5.1, which is on probability distributions. Probability distribution. It is a description that gives the probability for each value of the random variable. Typically we use the letter X. So it's going to give the probability for each one. That's all of them. So this distribution will represent the whole population of possible outcomes. Here we have a probability histogram. So you can see here that just according to the definition, it describes the probability for each X. So let me explain. This horizontal axis represents our random variables X. So our possible variables for X or values for X are the number of Mexican American jurors among 12 jurors. So you could have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or you could have 12. Those are all the possible values of X for a jury that has 12 members. And those are all the possible counts of Mexican Americans sitting on that jury. Okay, the vertical scale shows those probabilities for us. So it looks like to have 0, 1, 2, 3, even 4 and 5, and there's almost no probability of having exactly that many jurors. 6 starts to show up a little bit. The probability of having exactly 6 out of 12. Still really low though. Probability of having exactly 7 out of 12 is represented on this axis. Probability of having exactly 8 out of 12, exactly 9 out of 12, exactly 10 out of 12 is our highest probability. Probability of having exactly 11 out of 12, and then having all 12 out of 12. So the vertical scale, or the height of each bar, represents the probability. Let me erase all that now. Okay, we're taking the same data from this histogram. We're going to put it into this probability table. So you can see again from the definition, it describes the probabilities for all values of X. Okay, so these are all our possible values for X. These are all our X's. And these are all the heights of the bars in the histogram. So this can be a little more clear if what you're looking for is, well, what is that exact height, that probability of having exactly 8? And it looks like the probability of exactly 8 is 0.13. I got that from the table right here. So it's not that the histogram or the table is better than the other. It's just depends on what you're looking for. If you're looking to present your data to an audience who needs to just quickly see the shape of the distribution, then the histogram would be better. If you have an audience that needs each of those values, then maybe the table will be better. Or you can add those values onto the table. You could add the 0.29 right here at the top of that bar, and that might help. So just depending on your audience and what they need. Let me erase this. All right, I want to ask you a couple questions. Question number 1. Using the probability table, what is the probability of having exactly 7 Mexican American jurors on a jury? If you said 0.06, you got it right. Nice job. So what I'm emphasizing with that question is that these probabilities are if you have exactly 0, exactly 1, exactly 7. Let me try to explain through this next question. What is the probability of having 7 or 8 Mexican American juries on your jury? If you said 0.19, you got it right. That came from an or statement, 7 or 8, and we know that if the word is or, we use the addition rule for probabilities. So that came from 0.06 plus 0.13, which is 0.19. Looking at it, the bars here, this shaded region would be 0.19. The probability of randomly selecting a data value and it falling in this shaded region would be 0.19. If you're struggling wrapping your head around this, try thinking of it as a percent. That shaded red region is 19% of the whole histogram, or there's 19% chance that you randomly select a jury and it has 7 or 8 Mexican American jurors on it. All right, I'm going to go again. Next question. What is the probability of having at least 7 Mexican American jurors on your jury? I've actually got to get my calculator out to get this one. I'm adding up some numbers if you want a hint on what I'm doing. At least 7. Okay, ready for the right answer? If you put 0.96, or if you say 0.96, then you got it right. The probability of having at least 7 Mexican American jurors would be the probability of having exactly 7, or exactly 8, or exactly 9, or exactly 10, or exactly 11, or exactly 12. That is what at least 7 means. So you would add all these together, and there's a 96% chance, if you want to try to think about it that way at first, that a randomly selected jury will have at least 7 Mexican American jurors on the jury. Okay, and so think of it visually here. That shaded region represents 96% of this entire bell-shaped curve. It's another way to think about it. Whatever you need to do to wrap your mind around it, but then you do need to transfer your percentages back to probabilities or decimals if that's what you're being asked to do. Okay, hoping you're following. If not, rewind the video and start from this slide again, trying to explain the difference between exactly 7, 7 or 8, or at least 7. Okay, probability distributions, there need to be some requirements that are met before you can call your distribution a probability distribution. Number 1, there is a random variable x, and its values are associated with corresponding probabilities. And that is exactly what we have here. We have x equals 0, the probability of that x equals 0.00. Now we have x, I'll make it sub 1, equals 1. We have probability of x sub 1 equaling 0.00. So we have numerical random variables here called x, our x's, and their associated probabilities here. Okay, so requirement 1 is met. Requirement 2, the sum of all probabilities must be equal to 1. Okay, we know that this histogram represents all the possibilities, which means it's 100%, if you will, like the shaded region, 100% of all possibilities. Well, if we change it from 100%, so we move the decimal 2 places, then we're talking the probability of 1, which is an event that is certain to occur. So that is why the sum of all of these numbers in this column has to add up to 1, because a probability distribution has to address all possible outcomes, so it has to add to 1. Now, if you add all these up and you're off by, let's say, 100th of a percent, off by 100th, that might be okay still, because these may have been approximated already. So as long as when you add them up, you're between like 0.99 or 1.01, then you're good. Pre-rounding, your sum of probabilities should add up to exactly 1. Third and final requirement is that each probability value must be between 0 and 1 inclusive. And we already knew that because that's the definition of probabilities, or part of the definition. All probabilities are between 0 and 1 inclusive. Probability of any simple event A. Okay. All right. If you, in fact, have a probability distribution, so that means it meets those 3 requirements, then you can use the formulas below to calculate the parameters, or you can use technology. If you're being asked to find the mean of a probability distribution, you can use that formula there. I'm going to direct you toward using technology. I used to teach this by using these formulas, crunching them out by hand, but then a lot of the time in our learning environment was spent crunching the numbers and trying to figure out where we got a decimal place wrong. Now we're so lucky that the technology is not only readily available but accessible and reliable, that we like to turn to technology instead. That way we can spend more of our time interpreting what those results mean, not going, oh, where did you get x equals 0.04 from? If you are asked to find the variance, this is the formula. If you're asked to find the standard deviation of a probability distribution, okay, be very careful. These are the formulas that apply if you have a probability distribution, like on the last slide. If you're ever asked, so what do you expect the value of x to be? You'll do capital E for that, okay? So if anyone ever asks you, as a statistician, what do you expect the value of x to be? You're gonna use the mean, okay? It's always the mean. You always expect the mean to be the outcome. Unless, well, I won't go into it, but in this chapter with probability distributions, if they say, well, what do you expect the value of x to be? You go with the mean always. Okay, if you don't want to crunch these numbers or these parameters by hand, then you're going to use technology. You're going to go under Stat, Edit. That's always where we enter our data. You guys have been there before. Except this time you're going to have to enter your data into 2 different lists. The first list will be the x's, and the second list will be all the probabilities. Just like in that table, the first column was the x's and the second column was the probabilities. Then you'll hit Stat again, then you'll hit Calculate, then you'll open the program called One Variable Stats. Hopefully this rings a bell. You guys have run this program before. We're just going to run it a little differently. When we first practiced running One Variable Stats, it was off of one list. Right? L sub 1 was the default. But we're going to run One Variable Stats off 2 lists. And that'll be the x values and the probability of x values. And then this program will output for us the mean, the standard deviation. We can square the standard deviation to get the variance. And if asked what we expect the value of x to be, we'll go with the mean. All right, so let's try it. Find the mean, variance, standard deviation, and expected value of the probability distribution for the number of trials in 2 coin tosses. Give all answers to 2 decimals. Okay, mean, variance, standard deviation. Before, you may have thought, okay, I'll run One Variable Stats on my list 1. You're on the right train of thought. Expected value can be tacked on now because it's the same as the mean. But here's the key to know you have to do something a little different. You're being asked to find the mean, variance, standard deviation, and expected value of the probability distribution. That's chapter 5 now. So you'll run One Variable Stats off L1, which has to be the x values of your probability distribution, and off of L2, which is the corresponding probabilities of each x value. Okay, so we need to look at a table. We need the number of tails in 2 coin tosses. Okay, so you toss the coin, flip a coin 2 times, and the possible number of tails, maybe you got 0 tails. Maybe you got 1 tail. Maybe both times you toss the coin you got 2 tails. So those are our random variable x's. Those are all the possible outcomes if you flip a coin twice. Now we need to find their corresponding probabilities. Okay, well, let me erase my work over that. To find the corresponding probabilities, we can use a fraction. So out of 2 coin tosses, we want to look at what the probability of getting 0 tails would be. That's going to be a fraction, okay? Let's set up our sample space. Always start with the squiggly bracket for sample space. If we flipped the coin and got 0 tails, that would have meant we got heads then heads. Another option would have been heads then tails. Another option would have been tails then heads. And the last option would be tails then tails. Okay, so of our sample space here, 0 tails gives us our numerator. So there are, how many times do we have 0 tails in here? Just right here. If you flip heads then heads, that's when you have 0 tails. So that is 1 out of the 4 possibilities. 1 over 4. So that as a decimal is 0.25. You could leave it as 1/4 if you want. I just switched them to a decimal and I type them into L2. You can type it in as a fraction or a decimal. Let me show that again for the next one. Okay, erase that work. The next one is calculating a probability of getting 1 tail. Okay, it's going to be a fraction. The number of outcomes with 1 tail will be the numerator. And we already know the denominator, it's 4 outcomes. Heads, heads, tails, heads, heads, tails, and tails, tails. So it looks like 2 of the times, 2 out of the 4, we will get, flip a coin twice and get tails once. Okay, hope it's coming together for you now. The probability, this last one, probability of getting tails twice, it's only right here. It's 1 out of the 4 options. Okay, creating a table like this one here, you could be expected to do that. It's not very unreasonable. If the table were longer, if we were talking not coin tosses, but something else that has a lot larger probabilities and more exact probabilities, smaller probabilities rather, a lot more outcomes, then you'll often be given these probabilities. But for one like this, it's not unreasonable to construct. So, all right, so we have our table now. We're going to turn to our technology. So if you're using the TI like me, turn that on. We're going to hit Stat Edit and enter that data. And if you have old data, remember, just go up to the capital L sub 1, hit Clear, and hit Enter. All right, put your new data there, 0, 1, 2. It does need to be in order, matching up with the 0.25. 1 needs to match up with the 0.5, and 2 needs to match up with the 0.25. It's the only way we can tell our program how those are paired. Okay, we're going to hit Stat again, and arrow over to Calculate. One variable stats is our program. And now we have to run it with 2 lists. The way on my calculator that I run it with 2 lists, the first list is L sub 1, and then for the frequency list, I hit second and the number 2. Second and the number 2. If you're using an 83 or a program that doesn't ask you for the frequency list, then you will want to set up your screen to look like this. 1 variable stats, and in the same line you'll put L1 comma L2. The comma is above the number 7, okay? The comma is above the number 7. So to get the L1 on your screen, you just hit second and the number 1, then the comma. Then to get the L2 on your screen, you hit second and the number 2. Okay, if you run that correctly, then on your output screen, it has, on the very first line there, it has X bar equals 1. That is our mean, and it is our expected value, both of them. So notice that we're using mu instead of X bar, and the reason why is X bar is the mean of the sample, but mu is the mean of the whole population, and we have constructed all possible outcomes. So we're talking population parameters here. not just sample statistics like X bar. Can you erase that work? Okay, the next thing you have, let's do standard deviation next. On your screen you have lowercase sigma equals, and I'm going to go a couple extra decimal places, 707.1, I'll go with a 1 rounding up there. So your standard deviation to 2 decimals is right here, sigma equals 0.71. Now let me backtrack to variance. To get the variance, we need to square sigma. It's not already there for us on our output screen. We have to square it ourselves. So type that in and hit squared. Let's hope I brought enough digits with me. 0.7071 squared. And if I round that to 2 decimal places, I do get half, or 0.5. And the last thing they requested from us was the expected value of x, and we would expect the mean, so we would expect to get 1 tails when you flip a coin 2 times. Kind of makes sense. If you're asked, okay, someone's going to flip a coin twice, how many times are they going to get tails? Well, your best expected guess would be the mean, 1 tail, mean from right here. Okay. All right. Identifying unusual results. I want to back up a few slides. Wow, to this slide right here. Okay, I want to remind you about the when a probability value, so these ones, when it's less than 0.5, it's unlikely to occur. So all of these are less than 0.5. So if you're asked, what's the probability of randomly selecting one jury and it having exactly 6 Mexican-American jurors, the probability would be 0.02, and you could then say that that is unlikely to occur because it is less than 0.05. Okay, just a reminder there. Let's go back to, this is where we were. Okay, the maximum unusual value, if it's not clear that it's less than 0.05, can be calculated by taking your mean and adding 2 standard deviations. And the minimum usual value can be found by taking your mean and subtracting 2 standard deviations. You guys have seen this before. It just looked like x bar plus or minus 2 lowercase s's. Remember, we were doing that. X bar was in the middle, and then every time you went up a standard deviation, it'd be x bar plus 1 standard deviation, x bar plus 2 standard deviations. In the other directions, x bar minus a standard deviation, x bar minus 2 standard deviations. And I'm going to go a third time just for completeness. Third time over here, x bar plus 2 standard deviations. And remember that this part right here, if we cut it off at 2 standard deviations, then everything we have in between there is considered usual, unordinary, or non-significant. And everything out here is considered unusual, unordinary, or statistically significant. Okay, so it's the same thing now, except notice instead of x bar, we're using mu, and that's because for probability distributions, we're talking the whole population. And we're using, instead of lowercase s, we're using lowercase sigma. Again, that's because x bar and s are for sample statistics, but chapter 5, probability distributions, is addressing all possible outcomes. Okay, so let me erase all of that. Identify the maximum and minimum usual values to the nearest tenth for the number of heads in 5 coin tosses. Would it be unusual to get 5 heads in 5 tosses? Okay, the table was constructed for us this time here. Would be a little bit harder to construct this one on our own, although not impossible. If you want to try it, open up your sample space and start with getting 5 heads if flipping your coin 5 times, and then decrease it all the way until you're at 5 tails. And then close your set, and you'll find that there are 32 possible outcomes, one of which has no heads. 5 of them would only have 1 head being flipped. 10 of them would have, 10 of them, yes, would have 2 heads in 5 flips. 10 of them would have 3 heads in 5 flips. 5 of them would have 4 heads in 5 flips, and one of those possible outcomes would have 5 heads in all 5 flips. That's that first one right there, 1 out of 32. Okay, so we are going to use technology to type in these into list 1. Let me erase some of this work. Okay, this is all going into L1, and then in L2, you can type it in as decimals, or you can let L2 do the arithmetic for you. Watch this. Try to do this with me. Hit Stat Edit. In list 1, you've got 0, 1, 2, 3, 4, and 5. Now in list 2, go to your first input, and instead of typing it as a decimal, just type 1 over 32, okay? So 1 divided by 32, and then hit enter. And it does the decimal for you. Nice trick, that'll save you a lot of time. Next one, hit 5 divided by 32. Next one, 10 divided by 32. Next one, 10 again divided by 32. Next one is 5 divided by 32 again. And finally, 1 divided by 32 again. Okay, we're going to now hit Stat Calculate and run one variable stats. We're going to run it off list 1 and list 2. And I just ran mine. The first thing on my output screen is x bar equals 2.5. Next thing I'll be interested in is population standard deviation, which is 1.11803, and so on. Okay, so to apply, to use this formula, we're going to plug x bar in for mu, and so 2.5, and 1.11803, and so on in for sigma. Okay, it looks like this. The 2 is because we have to go 2 standard deviations out to determine the maximum usual and the minimum usual. This came from our calculator, and so did this here. All right, if you want to pause the video and type those in carefully, please do so now. If you type those in correctly, you'll end up with accurate to the nearest tenth. You get 4.7 and 0.3. So the maximum usual value of heads when you flip a coin 5 times would be 4.7 heads. The minimum usual value of heads if you flip a coin 5 times would be 0.3. Anything above 4.7 or below 0.3 would be considered unusual. You can look at those on a number line if you're struggling to just visualize what we're talking about here. Okay, so these are x values. Anything in here would be considered usual. This is the max usual. This is the min usual. Anything out here would be considered unusual. I hope that helps. So our answer, well, let's address that question. Would it be unusual to get 5 heads in 5 tosses? Well, let me get a highlighter. 5 is right about here. 5. So that is past our max usual range. So the answer is yes. It would be unusual to get 5 heads in 5 tosses. It's because it's above our 4.7, which is the max usual number. All right, I would like you to pause this video now and try this example, please. Welcome back. Let's see how you did. If you calculated x bar, or we're using it as mu now, to be 1.45, you're on the right track. If your standard deviation came out as 1.116915395 and so on, you're you're doing this right so far. If your maximum usual value would then be 1.45 plus 2 standard deviations of 3.6838 and so on. That's nice, you have that right. Minimum usual value would be the mu minus 2 standard deviations, so negative 0.7838 and so on. All right, so we have our maximum usual, 3.6, I'll just say 3.7, and our minimum usual, negative 0.8. And so the question is, would it be unusual or not to randomly select 4 people and all 4 of them have voted? Well, 4 is outside of our usual range. This is our usual range in the middle here, and 4 is out here. So it would be unusual. So would it be unusual or not unusual? It would be unusual. 4 is outside of the range of ordinary values, making it unusual. Okay, now there is a chance that you didn't do any of that work and you got it right still. Well, you had a 50-50 chance, but there's an even easier way. And if you remember at a few moments ago, I rewound and I talked to you about probabilities being less than 0.05. Well, look at this right here. The probability of selecting 4 people and all exactly 4 of them having voted is 0.04. That is less than 0.05. So you could have immediately, just by looking at this line right here, you could have gone, oh, that's unusual. It's too low. It's unlikely to happen. Well, if you didn't catch it this time, maybe you'll catch it next time. And that concludes our discussion on section 5.1. My name is Emigh. Thank you for joining me, and I'll see you next time for our video on section 5.2.